Aquarium keepers have been telling the same story for over a century. They arrive in the morning to find fish missing from a tank, only to discover that an octopus from a completely different enclosure had snuck out at night, slithered across the floor to hunt, and returned to its own tank before dawn. For a long time, these were written off as tall tales. Then, in early 2016, an octopus named Inky broke out of his tank at the National Aquarium of New Zealand. He slipped out of his enclosure, crawled across the aquarium floor, squeezed into a narrow drain pipe, and traveled 50 meters down that pipe to the open ocean. To understand the physics required to do that, look at how biological movement works in our own bodies. Vertebrate muscle tissue has a strict mechanical limitation. It can only contract and pull. It cannot actively push or elongate itself. We get around this limitation by anchoring our muscles to rigid bones. Our bones act as levers, and our joints act as fulcrums, translating the pulling force of a contracting muscle into directed movement. Without those rigid fulcrums to pull against, a vertebrate muscle cannot re-elongate its antagonist. It has no way to reset for the next movement, making a coordinated 50-meter journey across a dry floor physically impossible by the standards of our own anatomy. An octopus does have exactly one solid structure inside its body, a small, hard beak similar to a parrot's, located at the center of its arms. Marine biologists use a simple rule. If that beak can fit through an opening, the entire animal can fit through it. This shape-shifting ability relies on a specific anatomical mechanism called a muscular hydrostat. This image shows cross-sections of a squid tentacle, elephant trunk, and lizard tongue. Unlike earthworms, which rely on large liquid-filled cavities, the arms of an octopus contain almost no empty space. Instead, they consist of a tightly packed three-dimensional array of muscle fibers acting as hydrostatic fluid. Because animal tissue is mostly water, it has a high bulk modulus. In physics terms, this means the mass of the arm is essentially incompressible. It operates under the principle of constant volume. It strongly resists any overall change to its total size. This diagram shows how that constant volume principle creates movement. When the octopus needs to squeeze into a narrow pipe, it fires its transverse and circular muscle fibers. Because the total volume cannot compress, a decrease in diameter forces the tissue to extend in length. The limitation of the tissue becomes its mechanical engine. By simply squeezing itself inward, the octopus propels itself forward. This diagram illustrates muscle arrangements in hydrostatic skeletons. To pull its mass forward, the octopus uses parallel longitudinal muscle fibers capable of super-elongation. Navigating sharp bends requires helical muscle fibers, wrapped in left and right-handed patterns. Firing these fibers generates torsion, twisting the arm. In an animal with a skeletal system, contraction affects the entire lever arm attached to a joint. In a muscular hydrostat, contraction happens on a highly localized scale. A small group of muscle fibers can alter the pressure and shape of a single millimeter of the arm instantly. The octopus does not have to rely on fixed hinge points like an elbow or a knee to change its direction. Bending, elongation, and twisting occur simultaneously at any point along the appendage. Every single millimeter of the animal serves as a potential joint, granting it nearly infinite degrees of physical freedom. A rigid skeleton uses the physical geometry of bones to amplify the displacement and velocity of a muscle contraction. A hydrostatic skeleton lacks levers, but it achieves mechanical amplification through its constant volume geometry. Because of the math governing a cylinder's volume, a small percentage decrease in the diameter of a squid tentacle produces an exponentially larger reaction. This diagram shows the direct output of that geometry. A reduction in diameter of just 25% yields nearly an 80% increase in the appendage's length. By harnessing this geometric relationship, the biology functions as an exponential amplifier, converting small, local muscle contractions into rapid, large-scale displacement. Inky the octopus successfully slipped into the ocean and was never seen again. But the mechanics of his escape left a very clear legacy. This image shows a jointless robotic manipulator lifting a water bottle. Robotics engineers are actively using the biology of the muscular hydrostat to design a radically new class of machines known as soft robots. By replicating this localized control, Engineers are building machines that possess dexterity and resilience to impact that hard, jointed robots cannot match. The octopus shows that the most intricate, complex movements don't necessarily require a rigid frame. They often come from abandoning the bone entirely.